Welcome to week one, officially. This is, of course, Introduction to Computers and Programming. I'm Professor Tom Craver. You should have read by now or watched the video for week 0. That will cover all of the syllabus stuff, what we're going to cover this semester, how each week by week should work, and where you should find these videos. And if you're watching this, then you found it. I'm going to jump right in. Today, we're going to talk about basically an introduction to computers, hardware and software, how they work, how they store data. We're going to get into binary and why that's important for writing programs. We're going to talk about how programs work, and we'll do a little tease on how to use the Python environment, specifically the idle environment as part of that, but we're going to start on Python in full next week. So at the end of this week, to just be ready for next week, you want to make sure you have that installed. So, as far as this lecture is concerned, anything in bold, especially underlined, is fair game for questions on a test, that kind of stuff. So let's jump right in. Computers. They are dumb. They do not do anything that they are not told to do, period, full stop. They can be programmed, which is a good thing, and it is our job as programmers to tell them what to do. And they will do whatever we tell them to, sometimes to a fault, because if we make a mistake, they will certainly make a mistake in executing those programs. What is a program? Well, it's a set of instructions that a computer follows to perform a task. Do this, print this, show this on the screen, open a window. When I click the little start button or the little Windows icon, make sure the menu pops up. When I click the Word icon, make sure that program launches. When I type and hit Control B, make sure the text is bold. Those are all commands that you would write in your program, and the computer ultimately executes them to make stuff happen. Video games, same thing. When I press my joystick this way, when I press the D-pad that way, when I press A-B, up, down, it does something. Programs are sometimes commonly referred to as software, not always. The end result is the software that we're going to make. The program, by definition, is really just the code that you're writing. A programmer, well, anybody who writes a program, pretty plain and simple. They're also known in the industry as software developers. So, parts of a computer, because these can be kind of important. There's hardware and there's software. Hardware is anything physical that makes up the computer. Could be the keyboard, could be the mouse, could be any of the workings on the inside of the computer, including things like the memory, the central processing unit. Some newer computers, the gaming computers especially now, have what are called graphical processing units, GPUs. Could involve your hard drives, anything inside it, that kind of stuff. That's your hardware. Software is basically anything that you're going to run, the programs that we're going to write. So hardware looks like this, right? It could be almost anything. Typically, when we talk about hardware, we talk about what's inside the computer. All the chips, the central processing unit, which is the brain of the operation, if you will, and the memory where things are stored temporarily. But also inside there, you'll have secondary storage devices, things like your hard drive. Okay. Older computers had floppy drives. The drive itself was certainly part of the hardware. And then any input device, keyboard, mouse, flight yoke, joystick, scanners, digital cameras, tablets, if you're playing a game, any game controller, your webcam. And if you think about even like in a grocery store, they walk around with scanners. Those scanners end up sending input to a different computer somewhere else, often wirelessly. It's still an input device. So that's the stuff going in to the computer itself. It gets processed by the central processing unit and moved around in memory, and then something is sent to an output device. That could be a screen, that could be a printer, including your speakers or your gaming headsets. Those are all output devices. So the CPU, I keep mentioning this, it is basically the brains of the operation. As I said, it is the part of the computer that actually runs everything, it executes commands and programs. It is the most important component, and nothing runs without it. In fact, even with a graphical processing unit, graphics codes aren't processed without the CPU being present to tell things to, hey, go use the GPU for that. They used to be big. If you look in your book, there's a picture of ENIAC, which was the world's first computer. It filled a gymnasium. Now, obviously, they're much smaller. Essentially, any iPhone, if you think about how small phones used to be. Think about the Razors. Think about your iPhone 5 or 6 way back. They were small. They are very small. They can get right down to basically, as long as a computer has a CPU, some memory, input and output devices, it's a computer. A microprocessor, that is essentially what runs a CPU. It's a bunch of little processing units that are located on the CPU itself, which is a chip. Sometimes there's more than one processor built into one actual chip. Memory. Main memory is where a computer runs and stores things while it's running. It's also any data that's associated with it. So if you've ever been working on a computer, typing a Word document, and invariably this has happened to some of you out there, I'm sure, you're typing, you never saved it to disk or saved it to the cloud, the computer gets turned off, somebody trips the power cord, you have a big storm, the power goes out, and you lost everything that you typed because you forgot to save it. That's because everything is run in what's called RAM, the random access memory, the main memory that the system uses. And it's temporary. It is only temporary. That's why we say it's volatile memory. It's temporary storage while a program is running, while the computer is on. And everything goes away once the computer is turned off. So that's why you have things like secondary storage devices. This can be, usually in most computers, it's a disk of some kind. Now, whether it's a physical hard drive inside the computer, or an SSD drive, which acts a lot like a hard drive, but is really just kind of a long-term memory storage. It's more digital, like a flash drive, than it is a spinning disk. But it's still a secondary storage device that holds stuff for much longer. And when you turn the computer off, when you turn it back on again, that information will still be there. You expect Windows to launch when you start your computer. You expect your documents to be there when you open a folder. That's why it's considered long-term storage, because when you turn a computer on and off, your files are all still going to be there until you choose to delete them. Whereas memory goes away as soon as the computer is turned off. Types of secondary memory, secondary storage, if you will, disk drives. They are physically like metal platters that magnetically encode data on a disk. It looks a lot like a record player. It spins around, but each individual disk, there's more than one on a spindle, and your little heads that read the disk go back and forth and go in and out to read the information across the entire disk surface, and there's more than one. Solid state drives are faster than disk drives. There are no moving parts. It's like a flash drive. It's like a thumb drive, if you will, only it's inside your computer, and they're usually much larger. Flash memory, your typical thumb drives, I think we've all seen them and used them. It's not a physical disk. It's portable. Again, it saves storage for you. It's stores your programs, stores your data, stores your files. Optical drives, old CD drives, DVD drives, that kind of stuff, still being used on some older computers and for long-term storage of various things. All right, input devices. Again, showed you the picture before. Your book has some great imagery on that too. Anything that's basically, that collects information and sends it to the CPU. So your keyboard, your mouse, if you have a tablet, a little pen and your drawing tablet, game controller, all these things are input devices. Touchscreens, you drag and drop something, or you just tap something on a screen. You go to McDonald's and they have the new touchscreen ordering, tap those, that's an input device. Disk drives can also sometimes be considered an input device when they load data in a program that's running into memory. You can actually read from a disk. We will be doing that later on in the semester. We're writing a program that's going to read input from a disk and then do something with it and then put some output out there. So they can be, but they're still considered long-term storage, but they can also function as an input device to a program for reading some data. Output devices. Again, anything that gets processed, it's read in by an input device, it gets processed by the CPU, and then it goes out somewhere for somebody to see a result. Generally speaking, it's the screen. Okay, it could be text, it could be image, it could be pictures, it could be a video, it could be audio, but generally speaking, it's the screen. Could be a printer, could be video output, could be almost anything. Sounds. Disk drives, again, and USB drives can be considered output devices because the data that's processed is sometimes sent to them. Generally speaking, they're still storage. So software, everything the computer does is controlled by software. So things like Word, even Windows, the player that's embedded into a YouTube page is considered software. Your web browser to go out to YouTube to see that page is considered software. And there's a couple different kinds of software. So there's system software and there's application software. Application software is a program that you use for doing everyday tasks. Again, Word, your email program if you're using Outlook, a game you might play, web browser. All these things are application software. That's different than system software. System software is stuff like your operating system. If you're running Windows or if you're running Mac, you have Mac OS. It's the stuff that controls the basic functions and operations of a computer. Okay, so it might be if you're a Windows person and you're heavily into knowing how Windows operates, every device in your computer has what's called a driver. And sometimes if you buy a new computer, the driver might be out of date. You got to update your mouse driver or update your game controller driver. Those are system software devices, okay, or system softwares. A utility program is things that enhance how you do things with a computer, or maybe safeguard data. So your antivirus program. It's not something you're going to use to actually actively do anything like build a document or create a video or surf the web, but it's not system software either. So it's stuff that works with your system to keep you safe, but it does certain things. Your backup utilities to back up your computer or back up your hard drive, whether it's done through the cloud or whatever. That's a utility program. Anything that helps you clean up disk space or installs those drivers for you could be a utility program. The driver itself is the utility program. And then there's things called software development tools, sometimes called SDKs or software development kits. They are used to help create programs, modify them, test them, that kind of stuff. The Python environment, the idle environment we're going to use, is considered a software development tool. So that's it about a systems and hardware, software, everything you need to know about a computer, at least as far as the basics go. Hopefully we're not boring you. Hopefully we're not going too fast for you as well. So how do computers store data? Everything, when it comes right down to it, is stored as either a 1 or a 0. Okay? A 1 or a 0 is called a binary digit. It's just those two values. When you throw a few of them together, 8 to be exact, you get what's called a byte. Again, a bit is one element. It's either a 1 or a 0. And a byte is equal to 8 bits. And these things, you think about a bit as a switch. It's either on or off. It's a 1 for on or a 0 for off. Okay? And that pattern going back and forth is all a computer can process. Because if you think about fundamental electronics, you either have electricity in a wire or you don't. If the power is on, there's electrical current there. On. 1. If there's not, it's off. 0. And that's all a computer can do, because a microprocessor is nothing more than just simple electrical current, on or off. So again, a bit, a binary digit is what it stands for. It's where they get bit from. It represents either one of two values, the 0 or the 1. And when you add 8 of those together, it's called a byte. And that byte, we'll see, can translate into letters, numbers, and other characters. The position of something, and we do these in terms of 1s and 0s, and it's done in terms of what's called like clock 2 math or base 2 math. Okay? And bytes, because there's 8 bits, can be assigned values from 0, everything being off and all zeros, to 255, which is all the bits as 1s or all of them on. To store a larger number or to store more than one letter, you have to use more than one byte. So every single character is a byte. Every single digit, not a 1 or a 0, not a bit, but every single digit, your 1 through 9 or your 0 through 9 on a keyboard are considered a character, just like an A or an X or a Q. And one character is 1 byte, represented by one of the numbers, one of the values, from 0 to 255. So it looks something like this to a computer, okay? 77, the value of 77. which translates into something to a computer, is actually like this. Off, on, off, on, off, on. Or, in another way, 01001101. The letter A, which is actually a 65 value, and we'll talk about that shortly, is 01000001. Or off, on, off, on. What the hell does all this mean? That's a good question. Again, this is how computers store things. This is how computers operate. At a fundamental level, everything comes down to these ones and zeros. And the further you get into programming and the more deep you get, especially if you start doing system software or utility software, you need to understand how these work. And as I said before, they're all ones or zeros, bits, and that's called binary. It's called binary because there's only two choices, your 1 or your 0. So this 1001101 that we have here, that translates into the number 157, and that means something to the computer. It's actually a higher level control code, but it still means something to the computer. Okay? How does that mean something? Again, we talk about base 2 math. So each one of those ones or zeros represents an actual value. So starting from right to left, you can see the first one on the right-hand side shows a 1 underneath it. And then again, your three ones in the middle are 4, 8, and 16. Again, reading from right to left just for the moment. And the far left one shows a value of 128 underneath that. What happens when you add these up? We get a 1 for the 128 column. We get a 1 for the 16, the 8, the 4, and the 1 column. If you were to add those values up, and just bear with me on the randomness, it seems, of the numbers. You have 128 plus 16 plus 8 plus 4 plus 1. And if you added those numbers up, you would get the 157. But why? Why does that equal that? Think about the way you do with regular numbers right now. If you were to write 157 and forget binary just for a moment, you would say that that 157, and you learned this back in the day, probably with some blocks or something in grade school, is 1 100, 5 10s, and 7 1s. And that gives you the 157. And what that's telling you is, in that first column, and I mean the right-handmost column, for 157 using base 10, that's the ones column. Well, once you have 9 ones, if you add one more to it, you don't have any more. You do have more ones, you have 10 ones, but we put that into the tens column. So we say we have 1 10 and 0 ones. And then again, you go through, after you hit 90 tens, you get one more set of 10, that gives you the hundreds column. So we've been doing this in our heads, and we learned it in grade school a long time ago. Now the difference is, instead of saying the first column can be 1 through 9, we're saying the first column can be 1 or 0. So the ones column is actually just 1 or 0, which means once you get more than 1, you go to the next column, which is the twos column. So I would technically write 2 in binary as 1 0. 0 0 0 0 0 0 1 0, but let's just call it 1 0 for now, because you'll have 1 2 and 0 1s. Similarly, if you wanted to say 3, that would be 1 1. You'd have 1 2 plus 1 1 gives you the 3. So again, now if you go through all of these and you keep going up, you have 1, again, going from right to left. The 1s column, the 2s column, the 4s column, the 8s, the 16s, the 32s, the 64s, and the 128s. And those are 8 bits. Together, if you were to add all of those up, it would equal 255. That's where we're getting this value from 0 to 255. Then it's down to the system software to convert what that means in English to the rest of the world, essentially. So, when a computer stores stuff, it's storing it in terms of bytes, in ones and zeros. Characters need to be converted then from that. I said earlier that 65 means A. A is a translation from an old table that was made long ago when computers were first coming out, called ASCII. That's how you pronounce ACSII, as ASCII. It's an acronym that I forget what it means right now, and I probably should have looked it up before I started the video. But it's a table of values where certain numbers correspond to certain letters or other characters. Because when you press the backspace key to delete a character, that still has to translate as something. When you can press Control B, that has to translate into something as something else. So ASCII was the original standard. It still is the standard. There's something new now called Unicode, because now we all want emojis and we all want these funky characters and everything else that's not just standard letters. Unicode has ASCII as a base, and it's compatible with ASCII, but it could also represent our emoji that are out there, and it could also represent characters for other languages, like the combination AE or the tilde over an N or that kind of stuff. So here's what an ASCII table looks like, okay? So again, if we say A is 65, and 65 is stored as 01000001, in binary at least, how do we get there? How do we get from one to the other and back again? Well, this table, and I grant you it's a little small, and you could go Google search an ASCII table, okay? But if you look at these are all in columns, so you get to the bottom of the first column, and it starts back over with 32. 32 in that second column there is the value for a space. Okay, and 32 would basically be 00010000 would be the 32. 65, if you look at the top of the third column there, 64 is the @ sign, and 65 is capital A, not to be confused with 97, which is a lowercase a. And if you look at the very, very end of the bottom column there on the right-hand side, 127 is delete. Let's not get into the hex right now, although you might see that on your lab this week. Now, this is just plain old positive values of numbers. To store negative numbers and what we call real numbers, or anything with a decimal point, the computers use the binary numbering system and a whole bunch of different encoding schemes. Ways of, you think about a decoder ring when you were a kid, or some kind of secret code language where you've got to look up different things. That's what an encoding system is. So negative numbers are encoded in something called a 2's complement, and real numbers, again, decimal point numbers, are encoded using something called a floating point notation. And we'll discuss that, and it's part of future labs to come. Actually, I think we'll see it, if not next week, then the week after for sure. We'll start using floating point notation and floats, as we call them for short, in programming. For now, you don't need to know how the 2's complement or the floating point notation work, but you need to know that they're there, and you need to know why they're there. Other kinds of data. Basically, there's anything that's digital describes any device that stores data as binary numbers. And again, we'll go back in time here a bit. We can talk about digital music, MP3s, that kind of stuff, stored as ones and zeros. You can have them on your flash drive. You can have them on a CD. You can have them on a lot of things. As opposed to a cassette tape, an 8-track tape, if you really want to go back, or records, which were stored as actual analog scratchings or metallic linings up of pieces of rust on plastic to store the audio recordings. Digital describes anything that's a 1 or a 0. Digital images, digital music are all composed of these 1s or 0s. Pixels in a digital image are converted to a binary number, representing the pixel's color. So you have a whole string of pixels. Each pixel is 1 byte. And the more pixels you have, the more detail you have in the picture. And the color can be from 0 to 255. And actually, it's actually multi-byte for each pixel, because you have a red value, a green value, and a blue value, and then you have a black and white value for shading purposes. So there's actually 4 bytes involved in each pixel. And again, each pixel, each color of each pixel is converted to a binary number representing that pixel's color times the number of pixels you have. Think about a 16 megapixel camera that has 16 million different pixels, and then all the compression that goes along with it. Oh, it's fun times. But if you're going to program the next software for the iPhone or the iPhone's camera, then you'll need to know these things. And that's why we're covering this in so much detail. So many times the question I get is why? Why do we need to know this stuff? Because fundamentally, when you really get down into it, this is an intro class. We're going to talk about Python. We're going to talk about writing Hello World. We're going to talk about manipulating some numbers and formatting them differently. And we're going to get some more advanced stuff too. We're not going to be writing system software. We're certainly not going to be writing the next camera system software or utility software for the iPhone. Not in this class. But when you get down to it down the road, this is how everything is stored. And you will need to know that. So how does a program work within all this? Because a CPU is designed to perform very simple functions. It moves a 1 or a 0 into memory and out of memory. When it really comes down to the nuts and bolts, all it's doing is moving information in a memory location from one spot to another. And the instructions that do that are 1s and 0s. So it understands that. It actually understands some machine language, assembly language, which is, again, some more English-like than 1s and 0s, but certainly not as English-like as Python or other languages are. So it understands each one of these, and every single CPU has its own instruction set that's different, which is why you can't just take a PlayStation disc and throw it in your computer or in your Xbox. That's why there is Word for Mac and Word for PC. Everything is slightly different. Now, Macs and PCs both have Intel chips inside, but it wasn't that long ago that Macs used to have a completely different processor made by Motorola. Smartphones nowadays have all kinds of different processors. You have a Snapdragon processor. You have all kinds of other processors. AMD, which is an Intel wannabe clone, has its own instruction sets that are so similar to Intel that you can buy them as your computer and it still runs Windows and it still runs all your Windows devices. So, but every CPU has its own instruction set, which means you've got to write system software that will carry out the right instructions for that particular CPU. And the only way to calculate things in a meaningful way, that CPU must be able to do multiple things at once and perform many operations quickly. So what happens is the program starts to execute. It's loaded into memory, and then it's copied and into RAM every time it needs to run or do something with it. And sometimes information comes in and out of that memory while it's running to do more things. So basically, as far as a computer works, is it comes in and it grabs an instruction from the program, decides how it's going to run that actual instruction and what operation it needs to do once it gets that information. Then it executes that instruction, and that all involves, hey, right now you need to go to memory and load this. Great, this says, eventually, when it starts to get enough of these instructions together, go to input and wait for input to finish. So I'm going to start typing my name. Luckily, I only have 4 characters in that. And the computer says, okay, now what do I do with this? Oh, well, each character is being typed. I see a T. Great. That's going to go out, and we're going to display that on the screen. Oh, I see a Q. Oops, he hit the delete key now. We're going to display the Q. Now we're going to remove the Q from the screen. He actually meant O. Okay, that kind of thing. And the computer executes all these things on the fly. And the amount of things that it's doing is actually incredible. Because if you slide and move your mouse in the process while you're typing, or if you accidentally move your palm on your touchpad while you're typing, the mouse is moving while the character you just typed is popping up on the screen, and all kinds of things are essentially happening at once. And if you're like me and you're playing a YouTube video or listening to some music in the background, then those are all processing. And our music, internet exceptions aside, our music doesn't stutter while the computer is playing it. Especially when I'm playing a local file, there's no stuttering involved. If it does stutter, that means the computer had way too many things to execute. And it does happen every once in a while. We have all experienced that from one time to another. But effectively, that's what's happening. The computer grabs the next instruction, and they're all threaded. You might hear of things called multi-threaded when you have more than one processor or more than one microprocessor within the CPU. And that's so you can do multiple things at a time. But when it comes down to it, the computer can actually only execute one function at a time. So we go from what the English programming is in a language like Python, down to something called assembly, which are, like I said before, really short commands. Move this to here. It's basically moving around functions of memory or other electrode type device stored things from one device to another in some cases. But assembly language is not exactly an easy language to learn. There's a command called move, M-O-V. There's move all, M-O-V-A-L. I can't even remember all the other instructions. There's only about a dozen instructions with assembly. Again, depending on the processor, each processor has its own set of instructions. But assembly language, while it used to be taught in a lot of computer science courses, is not exactly the easiest for people to write big code in. It requires a lot of details. So we write with other languages called high-level languages, like Python, like C#, like Java. Okay, and then there's an assembler that actually reads or interprets that code that we write and turns it into assembly language, and then it turns that into machine language for each CPU that we need. So your low-level languages, like assembly, are very close to machine language ones and zeros. The high-level languages allows us to write something a little more clear to us so we can share it with people, so I can read it when you submit it as a lab. Easier to read for most people. There's no real need to know how a CPU works. And in fact, for something like Java, where there's an interpreter available for every single platform, on Android, on iOS, on Apple TV, on some Samsung TVs, and some other smart TVs now, plus PCs and Macs on top of it. Java has an interpreter for everything, so the Java interpreter knows for each device that it's on what the instruction set is for that CPU. But the person writing the Java code doesn't really care, because if he says make a window and put these buttons and these boxes in it, then it will just do that. And the Java interpreter does that for the programmer. Okay, there are certain words that every language has that you are not allowed to use, or you're allowed to use them but for certain functions, and you can't use them for things like variable names. So they're called keywords. Those are predefined words that are used to write programs in a high-level programming language, like Python, for example. Print is one such word, and we'll learn how to use that fairly early on. Then there's operators. Things that you've seen before, pluses, minuses, equal signs, sometimes two equal signs together, greater than, less than, the usual matter of mathematical-like symbols that basically allow you to perform arithmetic or do comparisons and compare data in a program. Syntax, when we refer to syntax, we'll talk about syntax errors, and you guys will be frustrated by syntax errors quite a bit, I'm sure, as you go through not only this course, but your career in programming. It's the rules that are followed in a particular language. Every language has its own particular syntax. Java and C, for example, make you end every single command, every single line of code with a semicolon. Python doesn't do that. Python actually looks at indentations and tabs, whereas Java and C don't even care. You can write everything as a big run-on sentence. With few exceptions, you need one space here and there for some things, but spacing generally doesn't matter in some of those languages where it's really important for Python. And then a statement is an actual individual instruction that you would write. Print this word. Add these two numbers. Those are statements. So there's compilers and there's interpreters. A compiler, we'll start with that one, basically takes your code and translates that sometimes into a temporary file that then gets turned into a more machine language program. So it goes from English looking like code to a compiled object to an executable program that can be looked at and read and feed instructions to a CPU. That's done with a compiler. Then there's some other ones that are kind of interpreters. And effectively, Java is an interpreter because the interpreter reads the program and then just says, okay, here's what the program meant by this, and talks directly to the CPU. So an interpreter is kind of Python is one, because Java is another one. It interprets one instruction at a time, throws it out there, and the interpreter itself actually translates that for the CPU. Whereas there's no translating between, there is no machine language program that's written. When you write Python, you're writing this Python code, and that's it. the Python interpreter will talk to the CPU directly. Again, as opposed to, say, C or C++, for example, where you've got to write this code, throw it through a compiler that makes this object file, and then it gets turned into actual machine language itself in a second stage of the compiling process. Source code, another definition you need to know. It is basically all of the statements that you write. The program that you write is source code. There are a couple different kinds of errors we'll talk about. A syntax error prevents that code from even being read further or translated. You typed something wrong. I don't understand this. For your C and your Java people, every time you forget a semicolon, that's a syntax error, and the computer says, the compiler and interpreters say, can't read this, there's too many things wrong with the code, send it back. Grammar errors, if you will. As opposed to a runtime error that we'll talk about later on, which is, hey, you wrote their sentences correctly, but you just didn't use the there correctly. That kind of idea. So again, what happens here is you write a statement in some kind of high-level programming language. Print, hello Earthling, or whatever the case might be. Add these two numbers. That goes through an interpreter. That interpreter, basically, like a sign language interpreter or like any other language interpreter, will take your high-level programming language statements, change them into machine language, and tell the computer, tell the CPU, here, this is what I need you to do. So your print hello Earthling might actually turn into a couple dozen instructions in machine language, which is, again, why we're using higher-level languages, because they're easier for us to understand as humans and interpret and do things on our own. Whoever wrote Python and wrote the interpreter for Python knows machine language enough and can take our statements and turn it into CPU statements. That's how our programs work. That's how everything comes together under the hood. Real fast, I'll finish this all off with using Python. You have to install it on your computer, whether you got a Mac or a PC or a Linux box. You need to install it. Go out to the website. It's listed in our course listings. The interpreter can be used in two different modes. There's actually an interactive mode where you can just type statements one by one. We'll start off doing that, but then eventually we're going to actually start opening an editor and typing things in there. So we call that script mode. When you start Python in the interactive mode, you're going to see a prompt. That little prompt is just a little dash. It tells you that Python is waiting for you to type something. When you type it, if it is syntax free, it'll execute that statement and bring the same prompt up. So if your statement didn't say to put out any output, you'll actually type your statement, press return or enter, and then you'll see the prompt again, and it will look like nothing actually happened. As long as you don't get an error, then that's a good thing. The interactive mode is there so you can play around with some things and say, hey, is this an actual real statement? Somebody sent me this code. Is this actually, maybe it's not a long code. It's just, hey, I want to learn this new function. Are these the right variables to pass? Is this the right way of making this happen? And if you don't get an error, you know it's right. You can add it to your script. So what we'll do a lot of after the second week is we'll start writing statements. We'll first start writing statements in interactive mode. They won't be saved as a program. They're just run at that point, and they're not saved at all. But then we'll start using the actual idle programming environment to actually write some scripts, write some Python programs, save them. And when we save them, they should be saved with the .py extension, because that's the easiest way, it's the only way for the Python interpreter to actually understand that that's a Python file and I can run this. And then if you're using the terminal in a Mac, or if you're using the command prompt, or even the Python prompt on a Windows machine, you just type Python filename.py. We would call that filename.py, and it'll execute the way it's supposed to execute. So, lastly, the idle programming environment. Idle stands for Integrative Development Program. It's basically one single program that is used to write your Python code and test it all out. So this is installed when you install Python. So there's a few things that install. If you're on a Windows box or even a Mac, you'll get, from our terminal window I can just type, or my command prompt I can just type, whatever. And you can type Python filename.py and go. It understands and installs that. But then it also installs this environment, where it's a special kind of command window that looks like your regular command prompt, but it's the Python one, where you can type the commands like I said, or you can choose to say, hey, open me an editor and write your whole programs out. So it runs in a very interactive mode. You close the window, it goes away. It has different designs. Now, when you first load yours will be white. I like lighter text on a darker background, so I took my screenshot and chose this. So this is what your prompt looks like. There's 3 little arrows there that you can type with. You type your first statement and it goes. Looks kind of like that. Or, like I said, you can go to File, choose New File, and when that happens, it opens up a new window where you can start typing. It is basically a simple text editor at that point. You write your program, you go into the File menu and hit Save, and life moves on. That's what you will submit for your projects. We'll get into that as we get into Python. That's the first week. I hope you're all still awake. If you have any questions, available via email, I will open up a discussion board at some point too for general questions on each lecture. And of course, office hours on Monday mornings from 11 to noon, or ping me for another time, either virtual or Zoom. Again, go back to watch the week 0 video if you haven't yet. Look at the course content and the summary of what we're doing for this week and in this whole semester for that matter. And hope you learned something, and we'll see you next week.